As a machine learning engineer, you may have experienced this dilemma. You've cleaned and processed your data, and now it's time to train your machine learning model. Let's draw an example of what your graph might look like. For a data set with these following points as an example, you're probably expecting a graph that looks like this. However, after training your machine learning model, you find out that it looks like this. So obviously, the data is underfitting, and the model wasn't able to learn the training data well enough. So we can fix that by training the data for a longer amount of time. However, now it looks like this. It's fitting almost every single data point exactly. So it looks like the model has learned the training data a little too well. Well, why does this happen? In a previous video on our channel, we talked about how overfitting and underfitting can affect machine learning models. But let's dive deeper into the root cause of the problem, which is bias and variance. So what do those terms mean? Bias and variance are two types of error that can lead to underfitting or overfitting in machine learning models. Let's talk about bias first. Bias can be defined as the difference between the predicted values and the actual values, also known as the ground truth. When the bias is high, the model fails to recognize patterns in the data and it starts to oversimplify the data. When the data is oversimplified so much that it's not able to recognize patterns or complexities at all, we can call that underfitting. Let's talk about variance next. Variance can be defined as the variability in predictions for each value in the dataset. When the variance is high, the model basically memorizes all of the points in the training dataset instead of memorizing the overall complexity and patterns behind the data. When this happens, we call that overfitting. In short, a model with high bias and low variance will tend to underfit. And on the other hand, a model with high variance and low bias will tend to overfit. We don't want our graph to look like either one of these graphs. Ideally, we want a model that has both low bias and low variance. In other words, we want a model that is able to recognize complexities and patterns in the training data, but also on data that it hasn't seen before. This is known as the bias-variance trade-off. All right, let's take a closer look at a graph that you may have seen before that illustrates the bias-variance trade-off. This is a graph that shows how the total amount of error changes as model complexity increases. We can think of model complexity as a way to measure how well a model is able to recognize relationships and patterns in data. We notice that as the model complexity increases, the total amount of bias decreases. We also notice that as the model complexity increases, that the amount of variance increases. And as the variance and bias change, the total amount of error also changes. So our overall goal is to minimize both the variance and bias such that we can get the lowest amount of error. And that will usually be in this sweet spot right here. This is our ideal complexity. So in short, the best way to fix and prevent overfitting and underfitting is to find the ideal complexity of the model that allows you to reduce both variance and bias while also reducing the total amount of error. Thanks for watching, and as always, please remember to like and subscribe.